So let's get right into it. We all see these mind-boggling price tags for advanced military aircraft, right? But have you ever really stopped to think about why a single part can cost a fortune? Well, it's not just about the fancy electronics or super exotic metals. A huge, and I mean huge, part of the cost comes from something that sounds, well, surprisingly simple.
Get this. Somewhere between 40 and 60% of the entire cost to manufacture a high-performance composite part comes from just one phase of the process, the cutting and layering of the material. Yeah, you heard me right. It's a process called Ply Collation, and it is the absolute hidden giant when it comes to aerospace manufacturing costs.
So today we are going inside the clean room to really break down this super intricate process. Welcome to the Art of Assembly, where we're taking a deep dive into the world of high-performance composites. All right, here's our game plan. First, we'll tackle why these composites cost so darn much. Then, we'll see why the raw materials have to be handled with extreme care. After that, we'll get into the nitty-gritty, cutting the individual layers, or plies, with insane precision, the actual art of laying them all up, and finally, how the whole thing gets bagged up for the final cure. Okay, so let's jump right in with that massive cost driver. In the world of advanced manufacturing, it turns out that getting the raw materials into their final, perfect shape, well, that's where the real money is spent. And this process, Ply Collation, that's the culprit behind that giant 40 to 60% cost. You can think of it as a super high-stakes, incredibly high-tech version of papier-mâché. Every single layer has to be placed perfectly. Any tiny error can be absolutely catastrophic down the line, and that's precisely why it's so expensive. Now, before you can even think about laying up a part, you have to understand the material itself. And this is not something you can just, leave sitting out on a shelf. It demands a super strictly controlled environment from the moment it arrives to the moment it's cured. So the material we're talking about is called Prepreg. And the best way to think of it is like high-tech refrigerated cookie dough for engineers. Seriously, it's sheets of carbon fiber that are already pre-impregnated or soaked with a sticky resin. And just like cookie dough, it's perishable. It has to be stored in giant freezers to stop that resin from curing before you're ready. Handling this stuff is a whole science. You have to pull the roll from the freezer, but you can't just tear it open. You have to let it slowly warm up to room temperature. Why? Because if you open it while it's cold, moisture from the air will condense all over it, and that moisture can literally ruin the final part. Every single minute it's out of the freezer, what they call its out time, is tracked with incredible precision. And the room where all this magic happens? It's basically a clean room. It's air-conditioned and humidity controlled to fight against that invisible enemy, moisture. It even has a slight positive air pressure, so whenever a door opens, air pushes out instead of in. This keeps any stray dust or contaminants from getting in and creating a tiny weak spot in the part. All right, so once the material is properly thawed and inside the clean room, it is time to cut it into all the precise shapes needed to build our part. And this is where we see a huge shift from old-school, hands-on craftsmanship to modern robotic automation. For a long time, this was all done by hand with templates and knives. And for one-off jobs, it's cheap to get started, but man, is it slow. It's incredibly labor-intensive, and you end up wasting a lot of that super expensive prepreg. Automation, on the other hand, costs a fortune up front, but it is lightning fast, incredibly precise, and way more efficient with the material. And the technology here is just fascinating. I mean, you've got options like lasers and high-pressure water jets. But the most common tools you'll see are reciprocating knives, which work kind of like a high-speed jigsaw, and ultrasonic cutters, which vibrate at these incredibly high frequencies to just effortlessly slice right through the material. And here's where automation is just brilliant. Powerful software runs what are called nesting routines. It takes all the different ply shapes and arranges them on the sheet of material like a crazy, complex puzzle. The whole goal? To get the absolute most out of every single square inch and cut that expensive waste to almost nothing. So now that we have all of our pieces perfectly cut, they have to be assembled. This brings us to the layup, which is truly the heart of this entire operation. It's where all these flat 2D shapes are painstakingly layered to create our final 3D part. Now, you might be surprised to hear this, but despite all the cool automation, manual hand layup is still king for the most complex parts. You have highly skilled technicians placing each sticky ply onto a tool or a mold by hand. And to make sure they're perfectly accurate, laser systems will often project the exact outline of the ply right onto the surface, guiding their every move. It's painstaking work for sure, but for really tricky geometry, it's still unbeatable.
Now, for the bigger, simpler shapes, you bring in the heavy machinery. This is automated tape laying, or ATL. You've got this massive gantry-style machine that lays down these wide strips of composite tape at incredible speeds. Think of it like a giant, unbelievably precise printer, just building up a part layer by layer. It's absolutely perfect for things like huge aircraft wing skins.
Okay, but what about round parts? Things like rocket motor cases or pressure tanks. For that, you use a process called filament winding. Here, a continuous band of fiber is wound under really high tension onto a rotating mold, or a mandrel. Now, this tension is what makes the final part incredibly strong, but it's also its biggest weakness. You can't use it on parts that have concave curves because the tension in the fibers would just cause them to bridge straight across the gap. So, what do you do when you need the automation of tape laying, but you're dealing with complex curves that filament winding just can't handle? Well, you use a hybrid, something that takes the best of both worlds. This is where fiber placement becomes a total game changer. See, unlike filament winding's single high-tension band, a fiber placement machine controls dozens of individual strands, which are called toes. And here's the magic. It can cut and restart each of those toes independently, using almost no tension at all. This allows it to literally steer the fibers perfectly into complex and concave shapes that other automated methods just can't touch. All right, once all the layers are in place, the part still isn't finished, not by a long shot. Right now, it's just a stack of sticky, flexible material. Now it has to be prepared for its final transformation in a high-pressure oven or autoclave, and this is called the bagging process. This whole setup is like a multi-layered sandwich of specialized materials, and every single layer has a critical job. First, dams are placed around the part to keep the resin from flowing out. A peel ply goes on to create the perfect surface texture. Then there's a release film to keep everything from sticking together. The bleeder cloth is there to soak up any excess resin during the cure, while the breather cloth creates a path for all the air to escape. And finally, the whole shebang is sealed up tight inside a vacuum bag. And this is another cool area where material science is making this whole process easier. Newer prepregs are being developed with exactly the right amount of resin right from the start. They're called net resin systems, and they pretty much eliminate the need for most of that bleeder material, which really helps to simplify what is otherwise a very complicated and labor-intensive step. So, after seeing all of that, we really come to the fundamental question that defines modern composite manufacturing. Do you rely on the incredible speed and precision of automation, or do you bet on the unmatched dexterity and problem-solving skill of a human artisan? And the answer is, well, it depends. There is no single best method. The choice between doing it by hand, using tape laying, or using fiber placement is a really complex engineering decision. It all comes down to a careful analysis of the part's size, its complexity, and just how many of them you need to build. And that's really the key takeaway here. In the world of high-performance composites, the most cost-efficient process is always the one that is perfectly tailored to the part itself.